Thanks, Alex, for solving this. Okay. Yeah, it's my pleasure to introduce the second invited talk at this year's CHES. It's, as you've seen, as you can read, it's Eran Tromer. Let me say a few words about Eran. He's done a PhD at the Weizmann Institute in Israel and has been has had quite a journey in the world, like previous positions at the MIT, at Microsoft. You have been a professor at Tel Aviv University, and right now you're an associate research scientist at Columbia University, but quite also active in industry. Eran is a founder of Zlens Corporation and a founding scientist of the Zcash privacy preserving cryptocurrency. And right. And in terms of research, Eran is super broad, one of these figures that has been appearing in the CHES community and the TCC community, but not only there, but also like a couple of security conferences. So Eran has done it all. So I was surprised to see why there are so many technical problems with uploading the slides, but eventually it got resolved. Yeah. Okay, so he's been very well known for his unconventional side channel attacks, exploiting some weird leakage, which always is a surprise, special purpose, hardware breaking devices, but also more theory stuff like homomorphic encryption comes to my mind, but also zero knowledge proofs more recently. Okay, and today he's going to talk about from practice to theory. Sounds very exciting. How I learned to stop worrying and love the models. Eran, floor is yours.
Thank you. It's an honor to be here. And also I appreciate your patience as we were waiting for the beats to flow through. As they say, with great PowerPoint come great difficulties or some such. It's particularly an honor to have a chance to follow this in the footsteps of Yehuda Lindell, who gave a talk last crypto a few months ago about his journey from theory into practice. And while I've dabbled in that, I thought that there are some counterpoints about the back and forth that goes on between the two fields. And this will be a very subjective talks about the kind of experiences I've undergone as I came to fully appreciate the wonders of models and what they can do for us if we feed them and care for them. I have lots of material, very little time. Feel free to stop me. I don't mind skipping some slides in the interest of a good discussion. So just ask questions during or after, as you prefer. All right. Let's talk about side channel attacks. Side channel attacks are kind of the quintessential violation of models, right? We have our Turing machines, we have our Boolean circuits, and then we have the bloody reality where bits just leak all over the place. But if you haven't seen this before, let me show you some side channel attacks, some of the stuff we and others have been up to, and then we'll opine a bit about where this takes us. And let me actually start with something non-cryptographic, but very visceral. Which is the question that we all encounter. We are having a Zoom call and our colleagues seem slightly disengaged in the conversation. Now, is it because they are pondering words of wisdom, or is it because they are reading the email? I have this problem often. And it would be nice if we could figure out what the other side of the call is doing. Now, of course, they're not telling us, but the screen is. So the screen is rendering either a collaborative conversation or social media. And this screen is not intentionally shared with the counterpart in the conversation. But if you look carefully around you, you'll find all sorts of sensors that can observe the screen. Of course, there are webcams that could take pictures of the screens, but that's not very exciting because obviously whoever is reading their email will take care to not photograph their own screen doing that. But how about the microphones, right? We're having an audio conversation over the internet. So microphones are ubiquitous. They're picking up noise. And as it turns out, there is some noise coming from the electronics. Doing some very, very simple computation, in this case, feeding the screen pixels with the requisite energy. But nonetheless, as they're doing that, some capacitors are vibrating, some coils are whining, And if you look at the signal that is emanating and we plot it on a nice spectrogram, then you can see that different frequency components change over time. For example, let's take an extreme case of a screen that has some zebra stripes, then a black region, and some more zebra stripes. And you can actually, if you correctly demodulate the signal, you can see the zebra stripes, the black region, and the others in the acoustic emanations, in the noise generated by the screen and picked up by the microphone. Now, the presence of a signal by itself doesn't suffice. In this case, to actually exploit it, you need to do a sort of signal processing and then put it into some machine learning algorithm using neural networks in order to cope with a tremendous amount of noise and variability. I will skip straight to the bottom line. Yes, this works. We can robustly figure out what screen content is rendered on the other side of the call just by analyzing this leakage. Well, this basically has many practical ramifications if you happen to be chatting with me on a voice call. But beyond those, it's not just about screen content. It's also about real computation. Because the CPU inside the computer and its power supply and the memory chips and their power supply, everything there is changing its power consumption and its electromagnetic emanations as the computation proceeds, whatever the computation may be. And that can be picked up by adjacent sensors like the aforementioned microphone. So what if we could measure that leakage on the other side of a call and figure out what computation is happening? So in a paper presented at Usenix, we looked at several scenarios. Let me jump straight into some real computation. It can be artificial computation, like just a loop that does heavy stuff like multiplications versus just weighting. And then you can look at the resulting noise and the relevant frequencies. This difference between the two is easily distinguishable. And it also applies to many different computers of many different models. And it works through many different voice apps like Zoom and Skype and some gamer favorite apps, Google Hangouts. They all use different codecs, different transformations, but still the signal passes through. And it's not just any signal. It actually works for cryptographic signals. So here's one of the use cases. We looked at libgcrypt cryptographic library. It's open source, fairly popular. And we set up a laptop doing ECDSA signatures using libgcrypt while having an open voice over IP call. And well, it turns out that there are interesting things to observe. Because if we recall ECDSA, the interesting part here is the signing algorithm. And in the signing algorithm, there is a key point where the heavy computation is done. And that is an elliptic curve scalar by point multiplication of some group generator by a secret nonce K. As it happens, this K really is secret. If it leaks, the secret key can be deduced. Now, in the particular implementation of libgcrypt, it so happens that the multiplication takes variable amount of time. It's scanning the nonce for the leading zeros and skips those for efficiency's sake. And that means that a little bit of information about the execution time is leaking through a timing side channel. Now, we can observe the difference between different types of computation as gleaned before. And that gives us hope that we can indeed use this timing side channel to deduce the number of leading zeros in the nonce. As it happens, you can indeed do that sort of very crudely just by some simple signal processing, looking at the signal after some filters and AM demodulation. And then there is a point in the resulting demodulated signal where you can see that there's a valley of less energy corresponding to the signing operation. But it's extremely noisy. So we need some more techniques to repeat and amplify, reject outliers, And at the end of the day, we can indeed identify the cases where the nonce has many zeros, and that, as it turns out, suffices for key extraction. We can't recover the whole nonce through this channel, but having many examples of signatures whose nonces have many leading zeros through lattice attacks, in particular the improved ones of Albrecht and Henninger, suffices to extract the full key. So real machine, real software, real cryptographic algorithm, and the attack was just talking to someone whose computer is running that algorithm. That's pretty scary. Now, even scarier is an application to Counter-Strike. Now, for those of you who are either too old or too young to know Counter-Strike, that's a very popular first-person shooter game. It's the most popular in its class ever. There are tournaments with large sums of money. It's a serious thing. It hinges on the fact that when you roam the world, you don't know where your opponent is. So at any point, they could ambush you or backstab you. But of course, you're going to win, and then you need to express your glee at their expense, and that means having an open voice over IP connection, right? So there's a voice connection through which you can, as you can by now guess, record the noises made by the electronics of your counterparty and deduce what they're up to. As it turns out, 3D rendering is a fairly computationally expensive process, and the complexity of 3D rendering depends on what your opponent is looking at, their 3D frustum. And if you are moving in and out of that frustum, you can modulate that signal, and bottom line, you can learn where they're looking and then go around them and stab them in the back. I'll refer you to the full paper for the details, but I guess it's one way to monetize research. You can enlist to those competitions and try to make some money out of that. So going back to some older works, why go through voice over IP? Maybe we can just directly measure the acoustic signals through microphones. So you can just place your cell phone next to someone's computer and record the signals, or you can even do that at large distances. This is 10 meters away using a parabolic dish, using laser microphones. There are results that are even more striking. And all of these things boil down to the same point. Our computers leak information in inadvertent ways through, in this case, the acoustic and electromagnetic channels. And models that don't take this into account will give us a false sense of security, as is the case for many of the leading algorithms and that have been struck over various attacks in various supposedly secure implementations. Yes. So the question was, does it require an app that conveys the voice? So in the first few examples I gave, that requires some kind of voice over IP app. In principle, it could be done even if your cell phone is near the computer and recording. That is a lower signal quality, so we haven't looked at that very deeply. This last thing I showed, this does not require an app. This is just having someone, in this case, the computer at the end of the classroom doing some RSA encryption. The attacker is here with this parabolic dish and amplifier and some signal analysis, and they're just recording the noise from across the classroom and recovering the key. Correct. You might be muted, though. So I mentioned electromagnetic radiation. So this is a result I'm very proud of because of the apt name. We constructed the PITA, Portable Instrument for Trace Analysis, which is a piece of package electronics inside pita bread. And if you place that pita next to someone's laptop, as it happens, that blue thing is an antenna. And some of the other things are amplifiers, filters, digitizers, and the small repurposed video streamer running Linux that does the signal analysis. So you can place that next to someone's computer running a vulnerable version of the software. and extract their keys. So what else? Let's pause here to assess. Things are scary, right? We saw some acoustic attacks in electromagnetics. Of course, there are the classic power analysis attacks where you just measure the power consumption of someone's smart card or computer or whatever the device may be. Then there are more invasive attacks where you stick probes and measure wires directly. And there's the whole huge class of architectural and microarchitectural attacks where you exploit things like contention for shared memory resources. One process is accessing memory, thereby using up some units, some resources, slowing down the other. The other is you, the attacker. So you can learn when the first one is doing its thing. And that has been shown over and over to be exploitable. This kind of crosstalk between things on the same computer leaks information, and I won't have time to go into the many fascinating techniques for exploiting it. But everything starting from a dedicated, supposedly secure cryptography to systems level mechanisms like SGX has been repeatedly broken by these kind of mechanisms. And last but not least, there are attacks not merely on secrecy, but also on integrity. Now, of course, secrecy often reflects indirectly on integrity, because if someone steals your authentication keys or your passwords, there goes your integrity. But also there are low-level attacks like Rowhammer, by which certain memory access patterns can cause corruption of memory for other processes running on the same machine. And you can even do that from JavaScript. So you can go to a website that has the right JavaScript code, which doesn't have any special privileges, but it can access memory. And next thing you know, your operating system is compromised. It's pretty bad stuff. Questions? All right, so let's talk a little bit about side channel resilience and what we would do about all of this. So clearly, the root of the problem here was that our naive models, the one we learn and teach at the Intro to Computer Science, are blatant lies, right? The model of, we have a nice machine, it has input, processing, and output, or a Turing machine, or Boolean circuit, whatever your favorite abstraction is, do not reflect any of these. And so in a world where these things exist, the secrecy guarantees or integrity guarantees are all off. And we have to do something about it. And I think the first paper that tackled this heads on is the Shai Sahai Wagner seminal paper from '03, which gave us the following framework. It says, let's start with any computation modeled as a Boolean circuit. And of course, it could be subject to various bad attacks. So we're going to fix it. We're going to plug it into a circuit transformation that will give us a new circuit that is resilient against some class of attacks. So the idea is that the adversary would be allowed to pick the leakage function from some class. The leakage function operates on the wires of the circuit and tells the adversary the result. That is, for example, in our case, this would be some spectrogram representing the noise while the circuit is evaluated. And the transformer is supposed to build this transform circuit on the right-hand side such that the adversary doesn't really learn anything from that leakage, from their augmented view, taking into account that leakage. What does it doesn't learn anything mean? Well, the simulation paradigm, there is a simulator that interacts only with the designated nominal circuit and just makes up the leakage function, and was precisely the output of the leakage function. And the adversary can't even tell whether they are looking at the real world given the real leakage function or the simulated one given by the adversary. I'm skipping many details here, but this is the spirit of things. And that paper came with a construction for the specific case of T-wire leakage, also known probing leakage, which is basically the case where the adversary can learn up to T wires out of the circuit. The construction is very elegant. It basically does secret sharing of every logical wire into many physical wires, such that if you only learn up to T shares, then you cannot decode. Now, for a single wire, this is trivial, right? You just provide sufficiently many shares. T+1 would do for additive secret sharing. But where things become interesting is that you need to compute. You have two wires and you need to compute their XOR, or their AND is more interesting. So now you need some kind of gadget that somehow evolves the wires in a way that no choice of T wires among the whole gadget, not just individual logical wires, leaks anything that is not simulated. So it's very elegant, and the stateless case is fully specified here, basically. And the security proof is also very elegant and intuitive. The idea is that when the simulator runs, and whenever they ask for a value of the wire in the transformed circuit, if this is if the value of this wire is already implied by linear algebra on the wires previously queried, then the simulator answers with that inevitable result, and otherwise it picks at random. And this all works, it gives the right distribution and is indistinguishable. Amazing. So that sets the create a huge cottage industry of other kind of leakage models that reflect different scenarios and extend the models in various ways. For example, there is the Micali-Raisin only computation leaks information. There is the Hamming weight model used by practitioners, separable leakage, bounded leakage, and many others. I will not have time for anything approaching a comprehensive survey, but I do want to point out Goldreich and Ostrovsky's work on oblivious RAM, which in retrospect is an amazing leakage resilient mechanism against the leakage of memory addresses. And the leakage of memory addresses is actually exactly what happens in many of the microarchitectural attacks I mentioned, where crosstalk in accessing memory reveals what memory is accessed. So in this case too, the theorists had the grand vision that the practitioners took many years to realize. Of course, at the time, when we published the paper on cache attacks and AES, we referenced Goldreich and Ostrovsky and said that unfortunately it's not practical and too complicated. And many people in this room have been fixing that. So I think we're doing much better also on the constants of applying oblivious RAM to these mitigations. And I also want to call out another development I found really satisfying intellectually. One of the criticisms on the original ISW probing model was that in reality, the leakage is not really local. It's not learning a few wires, but often the leakage is learning some aggregate functions of all the wires in the circuit. Think of that electromagnetic measurement or the acoustic measurement from before. It wasn't focusing on a specific bit in the CPU. It was some weird aggregate function. So how can we protect against those if the model doesn't even capture them? And it would be nice to capture some kind of notion of leakage that can learn a lot of globally, but it's not so smart that it can learn everything. And something like low complexity classes, say AC0, seems intuitive like a good match. So it turns out that you can extend, you can follow the ISW model and achieve a construction that is resilient against AC0, provably. And curiously, the way it works is by relying on circuit complexity lower bounds. We know that computing parity is hard for AC0. So if we use parity as an encoding scheme, an adversary that can only observe AC0 leakages from the circuit, that is leakage which is an AC0 function applied to the circuit, cannot decode. Now, again, this is the intuition for a single wire. If you're going to compute many gates or many wires, you need to make sure that there's no way to do some global AC0 function on everything and try to decode from that something. You also have additional information from the inputs and outputs. Turns out you can do it, but originally we could only do it using trusted hardware components. And then there was some additional follow-up work. There was a nice work by Rothblum that showed how the trusted, by saying trusted, I mean leak-free, but very small components. And Rosenblum eliminated that, but in favor of an assumption, IPPP. And last year, it turns out that actually the original ISW construction was secure against AC0 all along. You just needed the right analysis. So open problem resolved, and the next one up is what goes beyond AC0. The original paper gave a general framework with AC0 as an example. Can we stretch beyond AC0 also without the minimal non-leaky hardware? Questions so far? All right, so moving on, let me talk about something completely different. Biochemistry. So I think biochemistry is great. I'm doing it all the time. And just to recall from your biology class, the basics of life is DNA, RNA, and proteins, right? We have DNA encoding the information in a robust way, and the proteins that are the active embodiment of that information that are interact with the physical world in various interesting ways, and there's RNA that mediates the two. And the beauty of it is that DNA can really be thought about as a digital message, and that's key to many of the processes underlying life and evolution. But it's also a way to store information. You can go back from DNA into the digital representation through a process called sequencing, which is nowadays very inexpensive. The human genome back in the day was a huge endeavor. Now you can buy a machine that does it. Keep it in your office, on your desk. And you can also easily replicate DNA. Oh, I see someone doing it right now. That's a great way to store information, right? You can make copies, you can read it out, and therefore DNA storage is an active field of research and has various applications. But what about proteins? Proteins are weird and messy. They don't have a small DNA of pretty much passive molecules. Rather, it's a larger DNA of very active molecules that tend to stick to each other and do weird stuff. This particular example seems to be very popular nowadays. What would you ever do with proteins? They're so hard to work with. There's even an XKCD about it, but if you don't believe XKCD, then let me invoke Francis Crick. So in a seminal talk and follow-up paper in '57, Francis Crick presented this amazing breakthrough in the conceptualization of the essence of biological systems through the lens of information. And he posited that we have these three ingredients, DNA, RNA, and protein, and the information flow between them only works in particular ways. This is called the central dogma of molecular biology. DNA can be duplicated, it can be transferred to RNA, and you can make proteins out of that. But that seminal paper explicitly conjectured that it never happens that proteins go back into DNA. That is, into a clean digital representation. So first I find this conceptualization, 1957, really striking. But also these diagrams look a bit familiar, right? We have something that is easy in one direction and hard in the other direction. Now, what do we do with that, right? So we have some core hardness, and there's a good reason to think that this hardness really is there. So that conjecture withstood 65 years of research, billions of dollars of biotech R&D, because if you could sequence proteins, it would make finding drugs and understanding systems so much easier. And in a sense, it withstood billions of years of evolution. Because if evolution had developed a way to pinpoint the sequences and reason about them, it could evade intruders much more efficiently. And yet it hasn't. So you might say that the evidence for hardness here is nearly as hard as that of LWE. Now, so there's a core of hardness. What will we do with it? Let's dig some more into what's exactly is easy and hard. Well, we can read proteins. Proteins do interact with the environment, and they affect digital reality around them, and biochemists manage to eventually read them. But the thing is, the process for doing so is macroscopic and destructive. You need like a whole milligram of these proteins, and you put them in a mass spec, which basically breaks it down and shoots them at a detector, and the detector figures out what's the energy of the fragments. And then you take the signal together and try to guess what could have caused that distribution of energy. But there's nothing left of the original other than those fragments. So there's kind of like a built-in self-destruct mechanism that, whenever you try to read out these proteins. So we have something that is unclonable and self-destructing in some sense. And there are things in cryptography that are like that primitives that have proven useful, that have a similar scent to them. In particular, the one-time tokens of the GKR04 one-time programs paper are basically that, right? They're tokens that encode two messages. You can read one of them, and then they are assumed to self-destruct, and you can, of course, not replicate them, otherwise this would be trivial. And if you only had such tokens, then you can build bounded execution software. We heard about that yesterday for some motivation. I won't repeat it, but there are many reasons to want to limit the number of times a piece of software will execute. Clearly, you cannot do it in the standard classical model. But here we have a biological, of course, you could try to do it using electronics and tamper-proof electronics, right? You can have a device that is very, very secure in the requisite sense, and it doesn't have any of the leakages that I showed you earlier, and hope that you got it right. But maybe instead we can build it on something that is more fundamental, like these conjectured properties of the biochemistry. So we need to capture what are these properties, and to move to a higher abstraction level. What we conjecture to obtain is what we call a consumable tokens, parameterized by three parameters. One means, okay, V is the number of a key and message pairs that they can store. So I can take V pairs of a message protected by a key and put them in one test tube in the form of suitably constructed proteins. And then I will say a party, the honest party that knows a key KI can use that to somehow interact with the test tube and retrieve the message MI. That's the one in the parameterization. We're proactive about generalizing. But the dishonest party, well, we assume that the attacker has more power. Maybe they have the latest model of the mass spec. So they can read more messages, N messages, less than V. That would make it trivial, but there is some gap, and that can be exploited. The concrete realization of these, so very, very briefly, the idea is to synthesize proteins that have a payload part that conveys the message and a header that conveys the key. And then we mix them with many decoys, so it will be hard to get a nice clean sample that can be put into a mass spec. If you put a mixed sample into a mass spec, it basically gives you nothing useful. And then the honest retrieval would take a given key, consider the corresponding segment of the protein, and construct an antibody that latches onto that protein. That is something that labs can do. There's a standard procedure. So once you can latch into the correct proteins, you can pull those out and put them in your mass spec and read out the content. But any such interaction destroys some of the material in the test tube, and that is where the limit on the number of queries comes from. So this is one particular biochemical system that invokes the conjectured hardness in a concrete way. And then we can go ahead and try to argue about it. And this is where things become very interesting from the perspective of models and formalization. Well, obviously, we want to learn whether this system really has the properties we conjecture. That's an empirical question. But even before it becomes empirical, it's a modeling question, because what exactly are the properties? How do we capture them in a way that is empirically checkable? And what we do is we introduce an intermediate vector model that characterizes the conjectured evolution of the concentration of different proteins in the solution. And on one hand, that implies the primitive we need. And on the other hand, it lets us check whether concrete systems behave accordingly or can be brought to a state that contradicts the conjectured model. And right now we have our colleagues doing experiments in the wet lab in this spirit. On the other direction, given a simple primitive formally modeled, how do you build something useful out of it, like those bounded time executions? And we need tools to take some weak constant size properties and amplify them into strong functionalities of arbitrary size. Just like you would take a one-way function and build a PRG out of it and so much more. We want to play in this nice digital realm using a suitable abstraction. But how can we play nicely in the digital realm, taking things and composing them when the underlying system are messy proteins? So the right formalism needs to give the right. So the formalism needs to give the right composability properties, and the universal composability framework saves the day yet again. Sorry. Right. So the question was whether proteins are fragile, and it depends a lot on their environment, but with proper cooling and the right chemical environment, they are quite robust. So briefly, applications, it includes a relaxed notion of the one-time programs of GKR, as well as a notion of digital locker or low entropy encryption, which is basically an encryption scheme that makes sense even if the passwords have low entropy, because you can make the ciphertext self-destruct after a few attempts. So kind of like what you get when you log into Google, you're locked out after a few trials, by doing it in a non-interactive setting, where you're not talking to any server, you're just interacting with your local reality through this biochemistry. So I think there are many more quite interesting questions here about modeling and about additional primitives, but I will move on in the interest of time. Okay, again, to completely switch tracks, I want to talk about some other work that raises an interesting open question. So I'm basically abusing my talk here to pose an open question that I really need solved. But it's not just me that need it solved, because the motivating scenario is one where people are communicating privately and want to protect their privacy. Think about Signal or WhatsApp. Think about privacy-preserving blockchains like Zcash or Monero. We want to make sure that people can't eavesdrop on our messages. And there is some system, let's call it a bulletin board for simplicity, that collects messages. And they're sent by a sender, and you can make sure that they're encrypted. And then they are retrieved by the recipient. And we can make sure that the content is properly encrypted or randomized through encryption for simple messages or through zero knowledge proofs for things like the Zcash cryptocurrency. But that's not enough, because there's also traffic analysis. If people see who is paying whom, too much information leaks. The CIA director was famously quoted saying, "We kill people based on metadata." So let's talk about protecting the metadata. So on the sender side, there's a variety of techniques, things like sending your message through a mixnet. But on the recipient side, it's actually a non-trivial problem. How would the recipient learn what messages are addressed to them without disclosing that to others? The trivial solution is to just download the whole bulletin, every single message being sent, and do some kind of trial decryption to see what's relevant for them. Of course, that's completely impractical for large messages, even though some blockchains still use it because they're small enough. But the model we really want is to have some kind of detector service that serves the user and summarizes the blockchain on behalf of the user, a full node for the blockchain, if you will, serving a light client, for those familiar. But we want to obtain privacy against that detector. The detector should know what messages are addressed to the given recipient. So there are a few recent works on that. In practice, the Zcash people use some kind of a constant factor improved version of the naive scan just by discarding irrelevant information. There's a paper from last year that introduces decoys in a way that's oblivious to the detector and creates basically false positive, making deductions somewhat harder, but it's very not robust against active attacks or statistical analysis. And there's another paper that provides private signaling schemes, which basically implement the detector either using trusted hardware or using a multi-party committee, with the obvious drawbacks. And the question is, how can we do better? How can we get a single server without trusted hardware while making it efficient and furthermore achieving some stronger security notions that I haven't described yet? And as it turns out, this is possible. We have a recent paper where we construct this using fully homomorphic encryption. The idea is that the recipient would create an FHE key pair. The FHE public key would serve as a clue key, using which the senders would attach clues to every message. And whenever a sender wants to send a message to the recipient, they fetch their clue key, encrypt a bunch of ones under that clue key, and put that on the bulletin. And then when the detector working on behalf of that recipient is looking for the pink user's messages, I'm sorry, the animations are a bit wonky here. Okay. Then what they do is they take all of those ciphertext attached to every message and do an FHE recryption operation, that is decryption under FHE, in order to refresh the ciphertext, and then just take the end of that, and the result is an encryption of 1, in the case where indeed what we have is a bunch of encryptions of 1, right? We encrypt them, we get a bunch of 1s, we take the end, it's still 1. But what happens if the message was actually addressed to someone else? Then this recryption operation is using the wrong FHE evaluation key. And for the schemes we use, we get the natural property that recrypting under the wrong key gives you a random plain text. So some of those decrypted, some of these refreshed ciphertexts are likely to be encryptions of 0, therefore homomorphically evaluating the end by the detector gives a 0. At the end of the day, the detector gets vectors that is of ciphertext that are 0, 1, indicating what are the pertinent messages. That it can later be combined with additional techniques to create a digest that is sent to the recipient. And using generic FHE, it's completely impractical, but we use a variety of tricks, none of which I'll even mention, to make it so practical that it's even better than all other solutions, including those that use trusted hardware, and has very nice asymptotics, even for Bitcoin scale and beyond. Now, why am I mentioning all of this? So first, it's in order to give the warm, fuzzy feeling to all the people who have been working on FHE that, yes, it has yet another application, it makes people happy, and the Zcash people have been writing on how difficult this problem is, and they need it solved, and FHE saves the day. But the other reason is that we run into an interesting theoretical question as we were working on that, which is when we looked at an additional security property called denial of service resistance. So a denial of service attack on such a scheme is where an adversary sends a single message that is detected as pertinent by numerous recipients. But otherwise, an adversary can always spam someone by sending a single message to that someone. That's inevitable. But it shouldn't be the case that the adversary can send a wildcard clue that causes the message to be received by numerous recipients and induce load on all of them. That would create an aggregate load on the system, maybe overwhelm small clients, and overflow the scheme. It's really bad. And it's not theoretical. Prior schemes were trivially vulnerable to these attacks once identified. And the scheme I describe now actually resists the denial of service attacks, but only under the following weird conjecture. So here's the conjecture. It's a conjecture about LWE samples. It will be convenient to describe it in terms of Regev 05 encryption. So the setup is the following. The game is the following. We honestly generate two Regev 05 key pairs. That is a secret key and a bunch of LWE samples, and likewise another pair. We give those to the adversary and we say, hey, adversary, think about these as two Regev public keys and give me a ciphertext that decrypts to 0 under both of these. Oh, sorry. So the adversary doesn't know the secret keys. He cannot decrypt. What can I do? Well, they can do the trivial thing, in this case of giving the ciphertext in which the A vector is all 0. Okay, so let's rule that out. They can also do the trivial thing of encrypting a 0 to PK1 and hoping that it will come out 0 also when under PK2. Okay, so we look for a negligible advantage over that. Is there an adversary that can achieve over more than negligible advantage in this simple game? That's the question. There are many generalizations. I won't get into any of those, but even this cleanest version seems weird. It's not like any LWE assumption or other lattice assumption. It's more like a knowledge assumption. If anything, it's a bit reminiscent of the knowledge of knapsack of noisy inner products from the paper defining ECRHs and snarks. When combined with SIS, the intuition is that the adversary would only be able to construct zeros with high probability if they know what they're doing, if they know that they're putting together LWE samples. And if they know what they're doing, then that would violate SIS. But anyway, I would like to pose this both to assess the plausibility and its connection to other things known about lattices or knowledge assumptions in general. I added in the last minute an observation about Kolmogorov-Levin complexity in light of the other invited talk that dwelled on meta complexity. And I couldn't resist mentioning that it has yet more applications, including solving famous open problems in the realm of copyright law. As it turns out, lawyers are notoriously having trouble with the notion of copyright infringement, and in particular, the notion of substantial similarity. There, for example, this famous case of the Obama poster. Is the upper one derivative work? Is the lower one derivative work? Well, the lower one has to temporarily precede it, but if you didn't know that, and the tests that are applied are very heuristics and inconsistent, and there's whole scholarship about it. And it turns out that you can frame this problem in a way that looks intuitive to a cryptographer, using a sort of game with an adversarial advantage. And the way it's played is we have two parties, the producer and reproducer, corresponding to the plaintiff and defendant. And they each try to reconstruct the resulting image, one given just one given the whole original copyrighted work, and the other given just the non-copyrighted elements filtered out from it. And the point is that the non-copyrighted elements are kind of a description of a process that they could do. And if you look at it hard enough or read the full paper, you'll see that reasoning about the kind of processes that could be done to produce the copyrighted work looks a lot like reasoning about the complexity of describing a computation that produces a given string. Complexity of a computation, the size of the description of a computation that produces a given string is Kolmogorov complexity. Throw in some bounds on efficiency and you get Kolmogorov-Levin. And as it turns out, this beautifully falls into place. And we tried quite a battery of well-known legal cases to see whether this framework would give the same predictions, or at least explain them more intuitively, and it seems to stick. So again, the theorists have been doing something right all along. It just took a bit to realize. We are nearly out of time, right? Yay! Okay, so let me tell you about how to almost lose everyone's money by getting your model wrong. So this is my great mea culpa. So this is a kind of an anecdote that I hope any one of you wishing to make the Yud and Lidl side of the transition, going from theory into practice, will keep in mind. So it goes back to Zero Cash or Zcash. I assume many here are already familiar. The bottom line is it's a way to make blockchain transaction private by, instead of putting everyone's private information on the chain in order for the transaction to be verifiable, we just put a zero knowledge snug proof that the sender of the transaction already checked all there is to check. For those familiar, it follows the Sanders-Tashma approach, generalizes it in various ways, none of which I will dwell on today, except for one cool thing, well, one important thing. This uses ZK snarks. All of the properties of ZK snarks are highly critical here. The zero knowledge, the succinctness, non-interactiveness, soundness, and furthermore, knowledge soundness. The way to get those is using a structured reference string. So a CRS with private randomness. So how do we come up with that? Well, in the TCC paper, you would just assume the existence of that and give the algorithm for generating it. But in reality, you actually need a process by which to generate a string and have people trust it. So we built a protocol for the NPC dedicated for that, and then that protocol got executed by the commercial spin-off in a very striking way. There were 6 geographically distributed participants. It was recently revealed that one of them was Ed Snowden, and they all had dedicated machines, and they all used different procedures to monitor or protect those machines. Crucially, because this is an MPC with secret randomness for creating secret randomness SRS, secret randomness needed to be kept secret. So everybody had a lot of fun blowing up and burning and hammering at their computers at the end of this in order to make sure that hopefully at least one of the shares is destroyed, and that would have been enough. So that was part of the setup of the cryptocurrency, and it worked beautifully, and people started transacting, and large numbers were supposedly conveyed, but I can't really tell because it is privacy preserving. And there was even a publicly verifiable audit trail, so we can make sure the NPC was done correctly for the public parts of that. So for the soundness part, there are things you can verify. And my point is, we found out 3 years later that actually, oh, sorry, apparently I skipped a slide, but we did, oh no. Do the thing, please do the thing. It's a Mac. I can't do Mac things. So what we learned is that we had an oopsie, and our zero knowledge proof was not sound the way we generated the CRS. Concretely, what happened is there was a write-up we had in an unrelated paper of a variant of the Pinocchio scheme, and we had a typo there, copy and pasted some elements in the common reference string, assuming that G1 and G2 are symmetric, which they weren't in that case. And no one caught it for a long time because the proofs, they're very elegant in the GGM or AGM. But when you're working with the AGM, you need to keep track of what generators are available to the adversary, because the adversary is only on the hook to know the explanation of what the output as a linear combination of the generator they know. And if they know too many generators because you copy and pasted too much, then the proof falls down, and in fact leads to a real vulnerability. So fortunately, this was caught in time by Ariel Gabizon, who was doing a retroactive, a formal proof, and through a rather painful process, security was reinstated. The saving grace was that you could only cheat by knowing the requisite generators from the structured reference string, and very few people bothered downloading that structured reference string, and no one of them apparently abused that knowledge. So the moment it was realized, that file was taken down, and a major upgrade to the network went into planning and execution and happened in time. Then the sprout to sapling transition of Zcash closed that loophole. But it was very scary. And never do that. Make sure you get your models right and you appreciate the delicacies of things like AGM in this case. And by God, get your formal proofs formally proven before you deploy anything. Now, to help you do that, we have this thing, the zero knowledge proof standardization effort that aims to help understand what is out there in zero knowledge proof schemes and implementations, enabling interoperability between different implementations and new applications. We have a community reference, version 0.3 is just out, covering all of the above and more, and you're welcome to contribute. This is the last in-person ZK proof from before the pandemic, but the next one is next week in Tel Aviv. So drop by. We can use all the help we can get. And I think this would be a good time to conclude. So happy to take any questions for the remaining time.
Yeah, thanks, Eran. Questions, comments? We have time for a couple of them. Take the microphone, Evgeny. It's coming.
Non-technical question, but I'm curious. People are always saying that this blockchain is like decentralized, blah, blah, blah. So I assume somebody like Ariel or somebody last trusters would actually steal money from a lot of people. I assume it wouldn't have worked in practice. So some who do really believe in this, right? Because people like stop blockchain with like probably some kind of special instruction, like to reverse some transactions. I mean, do you really believe that this, well, in this particular case, this blockchain thing would, I mean, actually delivers on this decentralized thing? I kind of feel like social engineering would stop this kind of attacks actually to be effective in the real world. I mean, even if the bug was exploited.
So that's a great question, and in a sense, there is some stress here between security in the sense of integrity and security in the sense of privacy. Because in the cases of that Bitcoin and its friend had bugs, they were easy to notice because everything is in plain text, and you can observe that some wraparound minting just happened. If everything is properly protected by encryption and zero knowledge proofs, then some forms of bugs might not even be observable. I mean, may be provably unobservable by polynomial time auditors. And so there are good questions about how do you build built-in suspenders mechanisms, where it's basically combiners, where you for the finicky part of the scheme, you have something else that would be able to detect when they go wrong.
I've actually a question that somebody sent me over WhatsApp. I can ask it and read it out. So what do you think about the relevance of these leakage models to practice? Are they actually used in practice? And if not, why not?
So practitioners in the hardware world have their own view of things, their own culture and their own library of mitigations they like to use. And I haven't seen as much transfer between the two worlds as I hoped for, partially because the TCC compilers tend to be not efficient enough. Nonetheless, the analysis techniques developed for these ought to be employed even for the real world techniques. So there should be clarity about what is being protected against and why does it work. And there have been many failure modes by very secure chips that actually were not secure because the implicit adversarial model was not expensive enough. Still, there's a lot more room for convergence.
Yeah, so what do you think of the complementary viewpoint of, like, you know, implementing the ideal black box through other means that are non-cryptographic? So which is what I think some of the practitioners would like to do, like, you know, just to use formal verification to make sure that there's no side channel or something like that.
So I think formal verification is complementary and rarely in competition. The cryptography here is more about ensuring that particular computations correctly executed the thing that was formally verified.
Right.
And in fact, we just had a couple of works about these connections showing how cryptography can reason about formal methods and prove, for example, in zero knowledge that a vulnerability does or does not exist in a given piece of code. By reasoning about SAT solvers and resolution proofs and things like that. That said, for these complex protocols like the one I just described, certainly system-wide formal verification rather than just that of individual components is called for. And it does stretch the current limits of formal verification, so open problems galore.
Any more questions? Okay, yeah. Thanks, Eran. It was a fantastic talk.